So here's the basics of identifying quadratic functions given a graph or a table. So I first want to start by identifying what it looks like to be linear or exponential. From a table, we know that linear follows a consistent difference. So the x's change by a regular amount and the y's change by a regular amount, and we call it the slope. So in this case, my slope here is the change of y over change of x. In this case is -1/3. So if we're able to identify a common difference, we're able to identify it's linear. Let me skip the new thing. It's a little mismatched, but exponential is this one. So I know that it's exponential if my x's are consistent and there's a common ratio. We say multiplier. If there's a common multiplier, times 3 times 3 times 3, even times a half, even if it's a divider, and I'm going to put that in parentheses. That is informal. We never really talk about dividers. Common multiplier, because that's what it means to be exponential. It's times 3 x amount of times, a certain amount of times. So multiplying forever and ever and ever. So that's the old stuff. How to identify linear or exponential. I'm going to skip quadratic and come right back to it. So I want to identify these. Is there a common difference or multiplier? Well, first of all, we notice that my x's are consistent. 1, 1, 1, 1. And it's important to notice that it's the same throughout. So plus 1s. Common. Okay, what about the bottom? All right, well, this is, I don't know a multiplier, so let's check a difference. This is down 3, down 3, down 3, down 3. So if it is consistent, we look back up and say, what does it take if it's a common difference? Linear. So we would say this is linear. I also want to point out that my slope would be -3/1. Change of y over change of x. All right. B. What do we see here? So I see that it's plus 1, plus 1, plus 1, plus 1 consistently. And then my bottoms are, well, if it was a difference, it'd be plus 1. But then this is plus 2. So it can't be linear. So of my options, linear, quadratic, or exponential, I can cross out linear. I don't know about quadratic yet because I didn't teach it to you, but exponential, let's check that. Exponential would be a common multiplier. I'm going to highlight that. Okay? So if this wasn't plus, it might be times. Times 1 times what is 2 times 2 times 2 times 2 times 2. So it is in fact exponential. And I know my multiplier is 2. It's 2 raised to x. I don't know what my starting value is, but I know that my multiplier is 2. Okay? So then let's look at this one. For this one, I see, well, if this was a difference, it'd be -1, and then I see +1. So that doesn't work. Is there a multiplier? Well, no, it'd be half, and then I see that it goes from negative to positive. So by process of elimination, we could say that it is quadratic or neither, or none of the above. So we've seen a good example of linear. We've seen a good example of quadratic. Let's look at, of exponential. Let's look at what quadratic would look like. Quadratic is called second difference. Now it's not a very straightforward concept, but hopefully it's clear once I explain it. So first of all, my x's are changing constantly, plus 1s. And then I look to see, could it be linear? Well, if it were linear, there would be a common difference between my y's. Well, what is the difference between my y's? This is going down 1, then it goes up 1, then it goes up 3, and then it goes up 5. That is not consistent at all. -1 plus 1 plus 3 plus 5. There is no common difference, so it's not linear. There's also no good multiplier. But, we say there's a common second difference. So if I were to list the differences from the one y to the next, and then I were to look at the differences between them, it's a common difference there. So we see that from this to this to this to this to this, it's minus 1, plus 1, plus 3, plus 5. There's a pattern in here. Each of these are increasing. So the next one would be plus 7, plus 9, plus 11, plus 13. See, each difference is increasing by 2. So let's see this one. So if this were linear, I would expect this common difference to be the same. It doesn't look exponential because I don't see an obvious multiplier. But let's see. This is plus 3, plus 5. And it turns out it's the same exact common difference as before. From here to here, it's plus 2, plus 2, plus 2. So I can conclude it's quadratic. If I was able to conclude nothing, it'd be nothing or neither. Let me see if I can identify another one. Let's look at this one. So again, my x's are changing consistently. My y's, this goes minus 6, minus 2, plus 2, plus 6. So it's the difference here. This is plus 4, plus 4, plus 4. Do you see how my second difference is the same? So I can say it is a quadratic. Okay? This is plus 2, plus 2, plus 2, plus 2. Linear. This is, oh, that's hard, but I see this is times 6. So I would check on my calculator, times 6 times 6. Going backwards, divide 6. All right, this is exponential. Okay, big picture. That's what we're looking at in the front. When I flip to the back, what we're trying to do is write a function. So we know that for my linear function, I need to find mx plus b. Now on the front, I found m. M is the common difference, the change in y over change in x. That's your m. Now b, it is 0 comma b. So if I ever find a 0 comma b, I just point at it and I name it. I use it. All right. If I don't see a 0, I need to work for it a little bit. Okay. Quadratic. For quadratic, if I give you 2 intercepts, I would use intercept form. If you find a vertex, remember vertex is a turning point, then you can find the vertex. For exponential, we know my common ratio or multiplier is your b value, okay? And then the 0a is your initial value, your a. So that's how you find your a and your b, and x is always raised to the exponent. So let me show you an example. So I first need to identify, what am I looking at? Well, I see that this is plus 2, plus 2, plus 2, plus 2s consistently, which seems to be linear, but let's just check. Oh no, this isn't linear. This is minus 12, minus 4, plus 4, plus 12. So this is plus 8, plus 8, plus 8. Ooh. So this, because it's consistent here, I would call it quadratic. So I would need to identify, do I see a turning point? Do I see a, or zeros? In this case, I see my zeros. My zeros are here, where y value is 0. If I were to graph this, I would be at 1, 2, 3, 4, 0, 5, 6, 7, 8, 0. And you know from your previous unit that I would be able to say y is equal to some a value, x, well, if this is x equals 4, it needs to be minus 4, x equals 8, x minus 8, minus not plus. Now I don't know an a value, but what I could do is I could pick any point and plug in, and I should be able to get my a value. So if I take this point and I plug in a 2, I get 2 minus 4, 2 minus 8, some a value equal to 12. 12 is equal to some a value times negative 2, negative 6. Oh, it looks like 12 is equal to a times 12. So that's a simple 1. This is tricky, not going to lie. For this one, I need to identify, what am I looking at? Well, my x's are plus 1s. My y's, it's either minus 8 or divide by 2, divide by 2, divide by 2, divide by 2. Oh, okay. Well, if I'm dividing by 2 and I said I need a multiplier, it's really timesing by 1/2 consistently. Okay, So I'm looking at exponential, and I know the formula is y is equal to a b x. I know b is my multiplier, so b is 1/2. So I need to find my a. Now my a is my 0 term, my initial term. And I see my initial is right here, 8, because it's 0 comma. Remember, 0 comma. Y-intercept is where x is 0. Okay, let's keep going. For this one, I see that my x's are +1s, and my y's looks like minus, or +2, +2. Oh, okay, good. +2 throughout. So I know it's linear. For linear, it's y equals mx plus b. I mean, I could use a different formula, but this is one people are most comfortable with. So my m is y's over x's, which in this case is +2 plus 1. Y is equal to 2x. Sorry. Y is equal to 2x. And then what is my b value? Well, my b value is 0 comma. So in this case, it's +1. All right. In this case, I have +1s on top. And then on bottom, I have, that's a -6, -2, +2, +6. Okay. So I have, let's check the second differences. +4, +4, +4. Oh, it's quadratic. So this is the example where I would be using, I would have to look for, well, the previous quadratic, I looked for either a turning point or zeros. In this case, I used the zeros. In this case, I found a turning point. Do you see how it went down, 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 up, up, up? If I were to graph this at 0, 3, I would see this. So I can see my turning point here. It's here. And do you see the symmetry around my turning point? That 0 is exactly in the middle. So I have a turning point of 0, 3. So I'm going to use y is equal to a x minus h squared plus k. And I know that y is equal to some a value x minus 0 plus 3. And what we would do is we would then take any other point, let's say 1, 5, and plug it in. So, squared. If I put in a 1 here, 1 squared is 1, so there's a missing a value, times 1 plus 3 equals 5. Minus 3 minus 3, a times 1 is equal to 2. Oh, a is 2. Okay.